Yeah, you should now have gotten a notification that we're recording this. So hello everybody to this virtual EPR meeting after a long month of waiting. Today we have the first tutorial and I'm very happy that this worked out. So our speaker is Nicholas Chilton. He did his undergrad at Monash University in Melbourne in Australia. Then he did his PhD in Manchester with Richard Winpenny and Eric McInnes. And then he basically stayed at Manchester with different fellowships and different awards. And if I read it correctly, he's now a senior lecturer at Manchester University. And he also recently got an ERC starting grant. You might also know him as the author of Phi and Magellan. And today he's talking about single molecule magnets, design, measurement, and theory. Nick, the stage is yours.
Thanks, Nino. So I hope then, if this is after such a long break, I hope this is the tonic that you're all after. Look, I'm happy to take this in whichever direction people wanted to go. I mean, I've got the set piece, but if you want to ask me questions at the end that whatever else, then I'm very happy to talk about that. So this is a talk that's, as the title suggests, about single molecule magnets, and we'll cover the background. So there's probably a lot that most of you already know as EPR experts or users at least, but hopefully there's a bit in here that will be interesting and new to you. So hopefully that's what we have this afternoon. Okay, so if I can change the slides by pressing buttons, there we go. Right, so just a very brief slide of motivation. I'm not going to harp on about this and why I make up things I write in proposals that may or may not happen. But at least the idea of single molecule magnets, or one of them, is that if we could have an entity that is much more compact and we can use it to record information, then we could do something productive and possibly make technologies that would be beneficial. So for instance, in the data centers that span the globe, run by the likes of Amazon and Google, that power the cloud, which is powering this conversation we're having right now, magnetic hard disk drives are what is storing all the information. So this is being recorded on the Zoom platform, probably in a cloud, and it will be on a hard drive somewhere physically in the world. And these are the cheapest way of storing vast amounts of digital data. And the technology is quite simple. You have a hard drive platter. These are the disks that are coated with a thin ferromagnetic alloy. This is an image, a scanning tunneling microscopy image of, or electron microscopy image of such a magnetic thin film. This is neodymium ion boron, but in reality, I think these days it's mainly cobalt platinum alloys that are used. And these different regions that are shaded in different colors would indicate different magnetic domains. And so on this hard disk, you can assign these different domains. You can magnetize them either out of the plane, and perhaps that would represent a binary one, or magnetize them into the plane, and that would represent a binary 0, for instance. Now, in actual hard drive technology, I only learned this recently, a few weeks ago, you actually magnetize blocks, and it's about a 2x10 block of magnetic grains that you magnetize in order to have a bit. And there's so much technology that actually goes into doing this, because you have, of course, statistical patterns of actually how many bits grains you magnetize to get this bit, and all kinds of stuff. There's a lot of really cool electronic engineering going into these devices. But the basic premise is you have magnetic domains that record information in their magnetic polarization. But the point is, you can't make these infinitely smaller. If you want to have more data in a single drive of the same form factor, you can't keep shrinking these infinitely. And that's because in these ferromagnetic alloys, the atoms need to talk to each other. It's the exchange interactions between the unpaired electrons on these atoms that give rise to the memory effect. So you can't just keep cutting them down smaller and smaller. And so here enters the idea of single molecule magnets. As chemists, we can think about molecules, and they're very, very tiny. And we can, of course, control properties with chemistry. So if we could use molecules for information storage, what possibly would the density be? So this is the first single molecule magnet, manganese 12, which was synthesized in the 80s and then recognized to be a single molecule magnet in the 90s. By the Florence Group, home of Dante Kiteshki, where you all know Dante as an EPR expert as well. And this molecule is roughly 20 angstroms across, and so 2 nanometers square roughly. So back of the envelope, we're talking 4 square nanometers per bit. So that many square inches per bit, and that translates to roughly about 20,000 gigabytes per square inch, and that's about 100 times better than current technology. So there is a significant motivation that if we could make materials that have these properties, we could do something useful with it. And so you can think about, right, can we make data centers 100 times smaller, or at least 100 times more efficient in storing information, and they, you know, have a positive impact on the world. So this is why I get out of bed in the morning. All right, so how does this work loosely? We'll go in through the details of this, of course, during this lecture, but the main background is we have some memory effect. And so the key experiment we have in magnetometry is a hysteresis experiment. And so this is where we change the external magnetic field and measure the magnetic polarization, or the magnetization, the net magnetization of a sample. So in positive magnetic fields, we can positively magnetize the sample, and as we reduce the field back towards zero, the magnetization is retained, and it requires a negative magnetic field, so a field in the opposite direction, in order to magnetize it in a negative direction. And then similarly, we can bring the field back to zero and maintain a negative polarization, so that in the zero field condition, we can have two possible states of this material. Therefore, we can store information, so up or down, or one or a zero. So this is the hysteresis property of permanent magnets, and single molecule magnets show the same. The problem, though, of course, with this particular material is that the temperature scale is ridiculously small. And so that's the real problem to exploiting this for any useful practical application. So we would ideally like to observe these properties up at room temperature, where your hard drives would like to be operating, or actually somewhat above room temperature, but there you go. Room temperature is a big enough step from 2 Kelvin anyway. Okay, so how does this work, this material? Or what do you need for single molecule magnetism? The first thing you need is a large magnetic moment. Unsurprisingly, you need molecules that are very magnetic if you want to have a magnetic memory. And in manganese 12, we can very loosely sketch the magnetic properties of this molecule. It's actually very complicated, but in a loose sketch, we have 12 ions, 12 manganese ions. There are a peripheral set, which are manganese 3s in orange. There is a central tetrahedron, which is manganese 4 in green. And these have different spins. These are all octahedral manganese ions. And so these have different spin ground states, okay, in octahedral crystal fields. And loosely speaking, the outer set are ferromagnetically coupled with each other, and the inner set are ferromagnetically coupled with each other. But between the two, there's antiferromagnetic coupling. So if you do all the vector sums for your spins, you get a total spin ground state of 10. And that's where the large magnetic moment of this molecule is coming from. The second thing you need is an axial magnetic anisotropy, which is the same thing as saying an axial zero field splitting in EPR language, and a bistable ground state. And so in this particular case, the spin 10 ground state is subjected to a uniaxial anisotropy in the terms with like a D parameter, let's say, and it has a substantial negative D. And so what that means is that we have the MS minus plus or minus 10 states lowest in energy, and sequentially increasing plus minus 9, 8, 7, so on, all the way up to MS0 at the top. And so here we have a negative magnetic anisotropy, and we have therefore enforced, if it's a perfect D, D is non-zero and E is 0, so there's no rhombic anisotropy, then we have a perfectly degenerate pairs of plus minus MS states. And so this is important to define the plus and minus magnetization directions of our 1 and 0 states. So just now that we've got a picture of the electronic structure in mind, and we're going to revisit this hysteresis diagram. So in full equilibrium, in zero magnetic fields, at some low temperature, we would have 50% of the population of our ensemble of molecules on one side of this diagram and 50% on the other. They are degenerate in energy, so we have equal populations. If we magnetize the sample, then the energy levels are biased, and so then we will have some shuffling or reshuffling of the molecules towards their lowest energy state. So at very low temperatures, we would then move to a fully magnetized state in one side of this potential well. If we then return to zero field, we return these states to their equilibrium energies, but for a single molecule magnet, there is some slow return to equilibrium of the populations, and so the population stays on one side, and so we have a net magnetization that is retained, and this is how we define our different states. And so the same is true when we go to the other side. We polarize with a negative field and we bias the levels the other way. We move all the population to the negative MS side, and we have a negative magnetization. and then we can come back to zero field, and then that population is maintained on the other side. And so this is where the property of the single molecule magnetism is coming from. So the relaxation rates, and this is the return of an out of equilibrium magnetic population to the equilibrium 50-50 in the ground states, okay? And that's associated with the process of the molecules traversing the excited energy levels and getting to the other side. So jumping over this sort of energy barrier. And so this is called the relaxation rate. We use the symbol tau in single molecule magnet communities. You'll be familiar with this as a T1 process. So this is a spin lattice type relaxation process that is dependent on temperature. And for this particular material and many single molecule magnets, the relaxation rate, or T1 inverse, is exponentially dependent on temperature, according to a very similar expression to the Arrhenius law. So this is very much like first order kinetics from undergraduate chemistry. So you have an energy barrier here and then the temperature there, where this prefactor is set essentially by the spin lattice interaction or the spin phonon coupling, and roughly tells you about the attempt frequency. So, or you can think about that as like the spin phonon collision rate in the lattice. So yeah, it's one of those sort of more ambiguous concepts, but we'll get onto it a little bit later, I hope. So for reference, manganese 12 has an effective barrier of about 42 wave numbers. And so we've seen that this effective barrier, so this is the height of the energy that it has to jump over, is related to or comes from the zero field splitting. And so the Hamiltonian, of course, is something like this for a perfect axial zero field splitting. And so you can simply work out what the total energy height of your barrier would be in this simple Hamiltonian, and it comes out being like dSz squared. And so this is a really nice simple form that tells you, well, the effective barrier scales as S squared. So let's make S really big, and then we've done a job of making the effective barrier huge. And that's, of course, what most people did for the first 20 or so years of this community, making very big high spin clusters. So here are a few examples of some amazing chemistry that was done. So spin 33/2, that's pretty big. Spin 51/2, yeah, that's pretty big. 83/2, 45, so that's 90/2. 120/2, spin 91. I mean, this is getting ridiculous. And so you'd think we'd have some pretty good single molecule magnets by now. And unfortunately, though, the experiments are a little bit damning in the sense that no, it doesn't work quite that simply. And unfortunately, you just don't get what you would expect. The effective barrier does not scale as S squared, unfortunately. And that's for a simple reason that really what you have to have is this anisotropy part, which is where you get the separation, right? That's the anisotropy. And what happens with these large polymetallic molecules is that you have the single ion or the local anisotropies of the ions, and they all point in different directions. And you have to somehow corral them all to point in the same direction in order to get the projection of all of that anisotropy onto the coupled spin ground state. So this is, you can, Benzini and Gateshki's EPR book has all those projection formulae for coupled spin ground states, and that tells you basically that it's really, really hard to do this, and that's why you just don't get these massive barriers. And so if we go back, it's really the D here that we have to maximize. That's the parameter if you want to tweak it to increase the effective barrier. It's the anisotropy. And anisotropy, as you all well know, means that the magnetic properties just depend on the orientation of the molecule with respect to the external field. So we have anisotropic G values in EPR, so on and so forth. And this is the same idea here. And so anisotropy must tell you something about a connection between the magnetic moment of the molecule and the structure, right? There's some spatial dependence or connection between these two. And there are two sources of electron magnetism that are of interest here. And so we have the intrinsic spin angular momentum of the electrons, which is a quantum mechanical phenomenon, and the orbital angular momentum. And it's the second one here, the orbital component, which involves motion in physical space. Now, via spin-orbit coupling, yes, the spin also does. We'll get to that later. But by and large, it's the orbital component of the magnetic moment, which is the one that dominates the anisotropy terms. And this is why, of course, spin-only radicals have very small anisotropic G values or zero field splittings if they're interacting, there's biradicals. Whereas when you go to transition metals, where you start having orbital degeneracies and things like this, you get much larger anisotropy. So it's the orbital part that's important. Okay, so we need to get some large orbital angular momentum, that's L, that we're going to use in this notation. And so the solution that's prevailed over the last 10 years or so is to use the lanthanides. Okay, and that's because in the lanthanides, more or less invariant of their chemical environment, we have degenerate 4f orbitals. And so this gives you a significant orbital angular momentum in the ground state. So for the example of dysprosium-3, which is a 4f9 complex, we have 5 unpaired electrons, and an L of 5, which corresponds to the term symbol H. And so this is a significantly large orbital component, along with a significant spin angular momentum. And then, of course, we're down at the bottom of the periodic table with a large S and a large L, so we have to consider spin-orbit coupling. And for the latter lanthanides, where you have a greater than half-filled shell, we have let's say aligned combination. So we have the J equals L plus S ground state. And so down here, so this is the spin orbit splitting, which gives us all the way from L minus S to L plus S. But for dysprosium, we have the L plus S ground state. And so we have the 15/2 ground state there, or ground spin orbit term. Once you put this thing in a molecule, this J multiplet, the degeneracy is removed. So once you lower the symmetry from spherical to whatever the heck you have in a molecule, you split your J15/2 state into, in this case, Kramer's doublets. This is a Kramer's ion by the crystal field. And so you can see here that this sort of diagram, or these states, is what we are going to be building our single molecule magnets with. That this is where the relaxation is all going to happen. So I mentioned here that this is a Kramer's ion. That's really nice because we are guaranteed in zero field to have a bistable ground state. There's always going to be a Kramer's doublet in zero field. Not so when you go to, say, holmium, which has actually a larger magnetic moment slightly than dysprosium, but it's non-Kramer's. And so in a low symmetry environment, you are very liable to get either a singlet or a significant or non-negligible splitting between your two states. And that means has all kinds of implications for magnetic properties. So the real question now is, once you have identified to use a lanthanide, how do you enforce axial anisotropy? Because of course that's the key thing. You have to have one direction that is unique that you're going to magnetize along, and that's going to be how you define your bit. How do you enforce axial anisotropy? And that's non-trivial, especially when the lanthanides have very flexible coordination modes and often are very high coordination numbers, and usually pick up any water molecules that are floating around if they can. That's tricky. And so maybe it goes without saying, but the anisotropy is determined by the crystal field, so the shape of the molecule that surrounds the ion. And as we've said, we want a negative axial anisotropy, and so therefore the rhombic components, or the low symmetry parts, or whatever you want to say, should be small. But also we want to try and have the largest possible projection of the total angular momentum, so that is the largest plus minus mj states as the ground states. So for instance, if we take the 15/2 example and we just put a simple D parameter on it, a negative D type thing, this is the kind of profile we would get, and this would give you a nice single molecule magnet. Conversely, if you have a positive type D, this would not be a single molecule magnet, because as you lower the temperature, you will be populating these states here, and as you apply a field, the excited states are going to cross very quickly and populate those, and you're going to have all kinds of mess. So this isn't going to give you nice hysteresis, whereas this would. So not only do you need to make sure it's axial, but you need to have the right axiality. You need to have the largest states lower, and ideally this nice steady ordering of the states, 15, 13, 11, so on and so forth. And that's not trivial at all, especially when we think about lanthanides. And we can't just use a simple zero field splitting Hamiltonian, unfortunately. The crystal field Hamiltonian has many, many terms, as Ilya alluded to in his talking about implementing it in spinach. And so there's no simple way of just saying, okay, I want this order of states. And so it was really in 2011, this paper from Reinhardt and Jeff Long in ChemSci and from Berkeley, that proposed this concept of using electrostatics, classical electrostatics, to design complexes. And so when we're talking about spin orbit states, we're talking about total angular momentum states of the 4f electrons. And so once we've coupled the spin and orbital momenta, the f electrons are all acting cohesively. So we're not talking about electrons in orbitals or anything like that anymore. These are the MJ states, and they are collective properties of the 4f electrons. And so these have aspherical and well-defined aspherical electron densities for the 4f electrons in a given MJ state. And these have been worked out analytically in the 80s. And that's a beautiful paper if you want to look it up, of mathematics and physics. It's really nice. Lots of Wigner-Eckart stuff if you're into it. And what you get are these beautiful shapes. And so for dysprosium, which is what we're looking at mostly, we have this property where on the lowest, so the smallest projections of the total angular momentum, so the plus minus 1/2 state, has what we call a prolate spheroid. So that's an elongated spherical distribution. And if you go to the most magnetic state, you have an oblate spheroid, so a compressed spherical distribution. And all the way in between, you have this nice smooth change between them. And so that's really nice because that enables you to very quickly just say, well, the complex we want is going to have charges along a single axis. Because if you put negative charges above and below a dysprosium, then just by classical electrostatics, this electron density distribution will be higher in energy, and this one will be lower in energy. And there's a nice smooth transition between all of them. So you'll get exactly the picture that I showed on this slide here, right? That's what you would ideally predict. Now, of course, making a 2-coordinate lanthanide complex is non-trivial, and there's much effort that's going into that and still continues to go into that. And hopefully one day that will be realized, but we'll see. But in the absence of that, many examples have popped up, but this was one of the ones that I was involved with reasonably early on in this piece. And this is a complex from the group of Yan Zheng in Xi'an. And what you have is clearly not a 2-coordinate complex. What you have is two negative alkoxides. These are tertiary butoxides above and below the dysprosium. So these are formally charged. And in the equatorial plane, you have neutral pyridine ligands. So electrostatically, this looks like it's a sort of 2-coordinate complex. And yeah, okay, there is, electrostatics can only take you so far, and then, you get into molecular orbital theory and all that stuff, which is the more real currency. But it works. So this is a calculation of the predicted energy splitting of the states, and this blue line is where the measurement put this barrier. So it does have a very large barrier, this particular molecule. These are the other molecules that it left in its dust. This is, of course, now being beaten. This is no longer a world record, but at the time it was quite a jump. And just for reference, that's where manganese 12 was. So this strategy does work. So going away from the multi-metallic high spin clusters towards the single ion high anisotropy approach does really do work. And there have been some other great examples. I'm not going to highlight too much research in this because it's mainly about a tutorial, but there have been some great examples of D-block things as well. So, single ion atoms, again, in linear type geometries where you get large unquenched orbital angular momentum, and also some examples in the solid state as well. So this is a really nice methodology. So we have a barrier here, but this is just a computation, right? There's no, this is not an experiment. So how do we know what these transitions are going on and what's actually happening? What's causing this relaxation? So relaxation is the return to equilibrium, as I've said, and it's mediated by spin-phonon coupling. And so we have a few basic fundamental transitions that are of importance, and I've greatly simplified all of this. Of course, many of you will know a lot more about this than I do. So the first one is what we call the direct interaction. And this is a single phonon process where a single phonon is scattered from a magnetic impurity or absorbed in that sense. Again, we talk about phonon occupation numbers and things like this in the solid state. So a single phonon is absorbed when it impinges on a magnetic impurity ion or a spin and transfers its energy to the spin manifold. And so the transition rate, gamma, between two different states, according to a single phonon interaction, is just proportional to the square element of the interaction Hamiltonian between the two states. So this is Fermi's golden rule type thing. So of course, the energy of this phonon has to match the energy gap that you're trying to hit. Okay, and so now, of course, you have to think about your phonon density of states and all kinds of things to really work this out. The second fundamental interaction is a two-phonon process where we have, say, the absorption and then emission of two different phonons. And then it's the energy difference of those two modes, that causes absorption or emission of energy from your spin cluster. Okay, and so this is a higher order process. You're now into second order perturbation theory, which can either be at the second order time dependent level or the second order in the interaction Hamiltonian, which is then taken at first order time dependent perturbation. And these are the so-called Raman 1 and Raman 2 mechanisms. But it looks something like this. You have two different interaction phonon Hamiltonians that are mixing state A with some intermediate state C, and then mixing state C with B to give you this effective A to B transition. And of course, that's proportional to the energy of that state as well. Okay, so those are the two fundamental interactions that we have with phonons, but in order to think about the overall relaxation processes, usually we see multiple transitions. And so in manganese 12, it's well known that we have sequential direct spin phonon transitions. So we just jump up by absorbing different quanta of vibrational energy as we go up the ladder, and then emit it as it comes down the other side. So we go up and then down. And so this is called collectively, it's the Orbach process, which is a multi-phonon process or a bunch of single phonon processes, whatever you want to say. And it has just like the Arrhenius law, it has an exponential dependence on temperature. And so this is where this effective barrier really comes from, okay? I should say that all of this stuff about spin phonon coupling and direct rates and Orbach transitions, this was all done in the 30s and 40s by Van Vleck and people who were working on EPR, right? This was all EPR line shapes and measuring T1 and in chromium impurities and things like this. Some really spectacular mathematics and physics that those guys did. And it's taken us a long time to try and relearn all of that, at least in the SMM community. So there's a whole lot of really good literature to go into. Of course, Abraham and Bellini has a nice summary. You know, if you've got that sitting on your desk, that does a good job of all of this. But of course, for lanthanides, we don't always see the same thing. So often what we see actually is that we don't get all the way to the top, but somehow we shortcut. But again, we see a similar temperature dependence for this process. So in lanthanides, we also see these Raman processes that are quite prevalent, and these have a different temperature dependence. So these have a power law dependence on temperature. So you can identify this quite readily by just measuring relaxation as a function of temperature and plotting it. And this is usually thought to be a two-phonon process between the ground doublet or within the ground doublet pair. But again, this could feasibly happen between any other pairs of states. It's just that usually we see it at low temperature where these are really the only states that are going to be involved. And that I haven't mentioned any field dependence of this. Of course, everything here is field dependent, and there are other transitions that can happen once you start applying large magnetic fields and things like this as well. So how do we go about measuring these things? Just a quick time check. Where are we? Okay, I think we're all right. So how do you measure relaxation? Conventionally, we use AC susceptibility measurements in this community. And so that's where we apply an oscillating magnetic field. And what that's doing is, of course, sloshing the energy states of our molecules from up, one side to the other. And so we're watching at how the equilibration of the populations of these states is changing under the AC field. And so it's measured with a lock-in measurement, just like you measure use modulation in EPR. So this is quite a sensitive technique and gives you really accurate results. So what happens though is that at some temperature or for a given frequency, the system can't equilibrate quick enough to keep up with the AC field. And so the signal that you have that's in phase with your applied field starts to drop, and then you develop an out of phase signal. And so it looks something like this as a function of frequency. So the blue is our in phase, and as you increase the frequency at a fixed temperature, it drops at some point and goes towards what we call the adiabatic susceptibility, which is where basically the system is not in contact with the thermal bath anymore. The system is not able to exchange energy. Sorry, I should say the chi-T here at low frequencies is the equilibrium or isothermal susceptibility. And then the out of phase peaks when you have this condition here, and from this peak we can measure the relaxation rate. Okay, there's a really nice recent review by Steve Blundell and his team if you want to look at more information about AC susceptibility. So this is all modeled usually under the Dubai model, which is an empirical model, but does the job very well. And we can extract the relaxation times or rates. But generally speaking, for molecules, we often or nearly always use what's called the generalized or modified Debye model. And this is where there's this extra alpha parameter that's come in here. And so this describes a distribution of relaxation times, and that's important. And so what happens is as alpha increases empirically, this is the outer phase peak chi double prime as a function of frequency. As you increase the distribution of the alpha parameter from 0 towards 1, you get a reduction in the peak and a broadening of that experimental observation. And so at alpha equals 0, we have an infinitely sharp, a delta distribution, a delta function. And at alpha equals 1, you have an infinitely broad distribution. So there would be no peak. You don't observe anything. And the underlying distribution for this particular function is actually being derived, and it looks something like this. This looks a bit odd. Actually, it turns out that this function looks very much like a log normal distribution. And so that's why it looks like this on a linear scale. And so as alpha increases, you broaden the distribution. It's very simple. And so recently, what we've done is had a look at this and tried to think about how you can extract estimated standard deviations, because basically for 30 years, people have been using this technique and just plotting exact rates and fitting exact parameters to these models. And that's not very useful if you're trying to compare things and understand what effects different chemical substitutions are happening. And it turns out that the alpha parameters in most molecules are sizable. You know, we're talking 0.2, 0.3, which actually gives you about an order of magnitude plus or minus uncertainty on your relaxation rates. So it's important to consider these. And what we've done is just take that distribution as a function of alpha and found the condition when we integrate symmetrically on a logarithmic scale, where does that match one standard deviation in the normal distribution. And from that, we're going to define how wide this estimated standard deviation is. Now, this is of course an approximation and it makes a lot of assumptions, but it's better than nothing. And so it's a good thing to do. Unsurprisingly, as you increase alpha, so as the distribution increases, you have to go further, you have to integrate further, so your error bars get bigger, and you get a function that looks something like this. My mathematics isn't good enough to find the analytical solution to this, so we did it numerically, but you get a good enough model for experimental purposes. And applying this model, we can see that the molecule I showed you before, which is the bis-tert-butoxide pentapyridine, this is its relaxation rate. It's a function of temperature. We have at high temperatures an Orbach type multi-single phonon process, and then at lower temperatures it transitions to a Raman type mechanism. So this is an exponential and this is a power law. They look very similar on these temperature scales, but you can distinguish them in other ways. And you can see that the error bars are nice and small on this, but if you make a very similar molecule where we've now changed, we've still got a tert-butoxide on the top, but the one on the bottom has been replaced by a chloride, so it's still electrostatically 2 negative charges above and below. And in the equatorial plane, instead of having pyridines, we have THF molecules. So it's very similar electrostatically. It's not quite as good because chloride is a much more diffuse charge, so whatever. But the point is the error bars on this are much, much bigger, which gives you much larger uncertainty on all the parameters that we're talking about here. And we think that's because if you look at the crystal structures, the ADPs or the thermal parameters here are much larger on this molecule on the right. So there is a larger distribution of structures in this crystalline material at the same temperature than this one over here. And so we think that has something to do with making these error bars bigger. But of course, there are so many assumptions in this model, but it's a way to start thinking about structural distributions and magnetic parameters. You can also use DC techniques, so magnetize at some finite field and temperature, remove the field, and then just watch the decay towards equilibrium. That can be done in zero field or non-zero fields, of course, and then fit that decay with a stretched exponential, which is very similar, of course, to what the EPR community is doing in pulsed EPR experiments. But again, we don't have to worry about diffusion process, spin diffusion that gives us special stretch parameters and things that I don't yet fully understand because I'm not a pulsed EPR guy. But we do know that there is some kind of distribution of relaxation times. And so if we again look at the distribution associated with the stretched exponential model, that's well defined. And again, we can perform the same trick to integrate and find this region of 1 standard deviation, and you can get the same idea of estimated standard deviations from stretched exponentials as well. Okay, so I mentioned EPR briefly. Of course, you could think about measuring T1 processes with EPR, pulsed EPR with inversion recovery, but any single molecule magnet should be EPR silent, without a doubt, absolutely. I mean, manganese 12 isn't, and that's because the zero field splitting is actually small enough with high frequency EPR. You can hit the different delta MS equals 1 transitions. But for these single molecule magnets we're talking about here, we have plus minus 15/2 Kramer's doublet ground states. So you're talking a delta MJ 15 transition, plus minus 15. And you know, that's really forbidden, really forbidden. And the energy separation to the first excited state is on the order of, in good single molecule magnets, on the order of 500 wave numbers. So you're talking terahertz to get that transition. Now, of course, terahertz EPR does exist. It's just really painful from everything I've ever seen. So it'd be really good if we could directly measure these gaps. You know, I'd love that, but it's very hard. So if anyone knows how to do, you know, EPR up to 600 odd wave numbers, that'd be nice. But nicely enough, for, you know, lithium compounds are often isostructural. So if you can make the corresponding gadolinium, erbium, ytterbium analog, for instance, of a dysprosium single molecule magnet, you usually will get gorgeous EPR spectra, rhombic often at the times, which gives you an ability to characterize geometry, crystal field states from a different perspective using EPR. And so there's a lot of complementary information you can get using EPR. So coming back to this molecule, we've got a really large barrier. We know at high temperatures it's doing single phonon jumps, what we think it's doing single phonon jumps to get over the top. So this looks like a good single molecule magnet. Can we make this a technology and make $1 million? Yeah, that's the position we were at. No, that's the flat answer. We can't, and that's because for most dysprosium single molecule magnets, we have these hysteresis profiles here. And this is lovely hysteresis at non-zero fields, but as soon as you hit 0, it crashes almost to zero magnetization. And so as soon as you switch off the field, you lose your information. Brilliant work, guys. Fantastic. That's not what you need. So this is a problem. So this is very fast relaxation. And this is believed to be, or know quite well, that this is quantum tunneling of the magnetization. And so this is an abrupt transition from one side of your energy barrier to another that was first identified for manganese 12. And this is temperature independent, broadly speaking, and is very efficient. So this is a resonant tunneling process. In many cases, we don't know whether it's coherent or incoherent, or exactly which states are involved, or what the role of phonons are. There are lots of questions for these kind of materials at this point, which we need to study in detail, but it's a blight on this community. Of course, it means that we also have quantum tunneling between excited states, and many people think, and it's an open question, of whether the UF barrier that we actually see is indeed just some phonon promotion, and then a tunneling event, and then phonon emission. So, and that would have an identical dependence on temperature, because this intermediate process is temperature independent. So we couldn't distinguish the two from an experiment. So are there any materials that do any better? For a long time, the answer was not really. Except say for one compound from Bill Evans' lab in 2011, which had hysteresis open up to 14 Kelvin, there was nothing really better. But then Dave Mills and Conrad Goodwin at Manchester made this particular molecule, which is the first example of an isolated dysprosocenium cation. Okay, so this is lovely chemistry. And here what you have are 2 cyclopentadienyl rings that sandwich a single dysprosium ion. So you've got the axial type charges with nothing in the equatorial plane. So that's quite nice. And surprisingly enough, well, I was very surprised, this material has hysteresis up to 60 Kelvin. And so that's really quite nice. And you can prove that that happens not just in the pure material, but also in dilute material, and you can show it in frozen solution phase as well. So it's not an artifact of some long-range communication. It is real. And these are the magnetic relaxation rates for this material. We have an Auerbach process at high temperatures, and now you can see actually that this is slightly curved on a log-log scale, and that's indicative of an exponential process. And this one down here is nice and straight, and that's indicative of a power law process on a log-log plot. So this is our Orbach region, and this is our Raman region, and there are some parameters that we have here. So now moving on to the sort of the last part of this, which is the theory side of it, in terms of understanding spin-phonon interactions, which is where my group's going, and other groups as well. For that paper, for this particular material, we decided to try an ab initio calculation of relaxation dynamics. And so our approach was to use DFT to optimize the geometry of the molecule and determine the normal modes of vibration. Okay, so this is gas phase. We're ignoring the fact that this actually exists in the solid state with phonons and all kinds of things. So pure gas phase, very simple. And then calculate the spin phonon coupling using CAS-SCF calculation. So these are multi-reference two-component relativistic calculations. Scalar relativistic and then spin orbit a posteriori. And then from that, we can calculate transition rates. And so these are the rates between any pair of states. This is a simple, basically Fermi's golden rule. We have how the vibrational mode is coupling the different states, okay, which we get from CAS-SCF. We're just using Boltzmann statistics for gas phase harmonic oscillators, conservation of energy, of course, for the vibrational mode and the transition. And then we're just going to plug on a Gaussian to say that our vibrational modes aren't indeed Dirac delta functions. They are broadened and they exist. There's some breadth, there's some dispersion of the phonon energies in our materials. And from that, once we have these gammas, which are between all 16 states of our 15/2 multiplet, we can evaluate the dynamics using a simple rate equation. And that worked reasonably well, given all the terrible approximations that we make in that previous slide to get this dashed line here. And so we can do a reasonable approximation of this high temperature region, which is nice. And we haven't really had a good crack at doing this yet. That's still on the cards because doing two phonon processes requires a lot more computation and a lot more modeling, and that's a lot harder. So we're still working on it, but hopefully sometime soon. And what this shows us is that indeed this molecule goes across the barrier like we thought it probably would, and we can evaluate the different transition rates between this. But the most promising or the most interesting question to me was which vibrations are most important, especially for these lower states here, which is where everything starts. And so it turns out that there are 4 vibrations that couple these two ground states, the ground state and first excited state strongly. There are 4 vibrational modes, and they all involve distortions of the CP rings out of the plane at the unsubstituted positions. Okay, so these are the CH groups, and it's those carbons that are moving the most. So we have the in phase and out of phase components, and then again, if I go to the next slide, the in phase and out of phase components, where the rings are in phase, but their relative motions are out of phase. And so we proposed that perhaps you could substitute these and affect the modes and make this slower. Okay, so make these groups heavier, stop them moving as much. Would that be good? Oh, I cut out the slides. Anyway, some people have done this. Jeff Long and Ben Harvey in the States have done this and made some good examples. And Richard Layfield in Sussex has also done one. And he's brought the temperature up to above liquid nitrogen now. So 80 Kelvin is where he showed magnetic hysteresis. But the real question is more detailed. So I think I have 2 more slides and then you can harass me for questions or tell me that was boring and you knew it all. So we've been studying dysprosocinium, this molecule here, in a lot more detail to try and understand what's really going on. Why is it so good? And so we've done a lot of INS spectroscopy with our colleagues in Parma and down at ISIS in Didcot. And this here is an experimental inelastic neutron scattering experiment where we're measuring the neutron-weighted phonon density of states. And so all these different regions are different incident energies of neutrons, and so we get different resolutions with the experiment. So we have nice sharp peaks down here, and they broaden out from instrumental reasons, not because the actual distributions themselves are any broader. And so then this here in red is the DFT calculation, a periodic DFT crystal calculation of the phonon modes, where we've used the same experimental broadenings that we have in the experiment. And we see a pretty good agreement, I would say. You know, I think that's pretty passable for modeling the phonon modes. There is some shifts, of course, but we can think about that. This is PBE, if anyone's a DFT person. Doing these with a hybrid functional, say PBE0, takes a heck of a long time. We're doing it for comparison now, but yeah, it's a lot. So we've got a lot of experimental information on this and single crystal experiments. I'm not going to go through all details. We've done single crystal NMR, single crystal AC, single crystal DC, decay, all kinds of stuff. And we've got all parameters, and we understand a whole lot about it. And basically, there are a few key things that are the take-home messages that we now know about this molecule, and therefore about single molecule magnets in general. Okay, so the recipe for high temperature or high performing single molecule magnets. You need a large crystal field splitting between your states. You need to separate these energy states a long way in order to make relaxation slow. So you need a strong axial crystal field potential. And as I discussed earlier on, that has to be uniaxial, ideally minimize rhombic interactions, so low symmetry interactions, and you need to have the right states as the ground states to begin with. So once you've got all of that, this is how you optimize or maximize. Then we need to have high energy intramolecular vibrations. And so this is why the dysprosium molecule is so good, is because you have these rigid C5 rings, and it takes a lot of energy to distort these. If you compare that to the other examples I showed with single atom donors, we had pyridine in an equatorial plane and then single atom terpetoxides. It doesn't take much energy to just sort of wiggle these a little bit around, and you greatly change the electronic structure. Whereas for the CP rings, you've got to distort an aromatic C5 ring. And so the energy scale of these distortions, and therefore modifying the crystal field potential via phonons, is a lot higher energy. So this is one thing that's very good, and why dysprosium is so good. The second thing you need is a small Debye temperature. So that is when the acoustic phonons basically plateau and we start then moving on towards the optical phonons. And that happens when you have low energy intermolecular vibrations. And so again, dysprosium works very well because essentially you've got this big ball of grease. If I go back to the picture, you've got 3 terp-butyl groups on each side. So you've got a whole lot of grease that's just packing this molecule away from everything else. And the counterion here is, go back to this, is massive and very weakly coordinating and covered in fluorine. And so essentially you have very weak interactions. These are electrostatic, so that's a negative charge, that's a positive charge, right? But that's basically it. You don't have maybe dispersion forces, but we don't have hydrogen bonding, we don't have pi-pi stacking, we don't have, small molecules that can interlock very nicely. These just sort of pack like big balls. They don't really, tessellate very well. So that all helps. And so having weak intermolecular interactions is a good thing. But really moving forward, so we've got a bunch of these molecules now, we need to work out the details of how the phonons interact with the spin system in order to try and design better molecules. And that means modeling solid state densities of states, doing a lot more INS and all kinds of things to understand it. So there's a lot more fun and games to come. Anyway, it's exciting to see how far this has come along in recent years. So that's me for today. These are the people who've contributed to the small amounts of research I've shown. I tried to keep it mainly tutorial, so I hope that was instructive. So many people at Manchester, of course, all my colleagues there. Tatiana at ISIS, who's involved in the INS spectroscopy. Yan Zheng and his postdoc Yu Song, or his former student Yu Song, for making some molecules, and the team at Palmer for working on the INS with us as well. And of course, money from these people have been very helpful, without whom I couldn't have done any of it. So thank you very much. Happy to take any questions.
Thanks, Nick. Now, if you have any questions, the best way to do this is if you go to your participants panel at the bottom, you can raise your hand digitally. It should have a button that says raise hand. And then I see you, and then I can unmute you, and then you can ask your question. Yeah.
Right. Awesome talk, Nick. I finally understood a few things. One comment, the people, you mentioned solid state DFT calculations of the phonon spectrum. A paper just came out in Science Advances like a couple of months ago. Who was it? Alessandra Lunghi and company did that. And they're also an order of magnitude out. So same as you. So they did their damnedest, and they're still an order of magnitude out. So this order of magnitude seems to be the domination. Nobody really knows where it's coming from.
Yeah, I mean, so there are two things to comment on that. They are looking, I think, if I know the paper correctly, and I might be misunderstanding, they are looking at vanadium spinning on half states, right? So they're looking at quite different electronic structures. So there's a whole different set of approximations and things that they might be doing there that are slightly different from us. Also, we haven't yet taken the full ab initio solid state phonon calculations and coupled them to the ab initio relaxation rates. That's in progress. You know, unsurprisingly, I think there are something like 4,000 calculations when you just consider the gas phase modes. So when you know, it's something like, it's an order of magnitude more. We're talking, you know, 20, 30,000 CASA-CFs that we have to do. So that's in progress, and I hope to have some information soon. I would hope that the order of magnitude gap decreases, but we'll see.
One other thing. So imagine that you do get that technology, right? So something that's of the scale of 100 angstroms, presumably because of the relaxation will never really go away. It will have to be remagnetized every now and then.
Sure.
For the information to be stored, so refreshed. And then, yeah, it's a dynamic memory. But of course, a dynamic memory with 100 angstrom unit size, you can buy on eBay. It's called a drum chip.
A what chip?
Where, well, dynamic RAM.
Oh,
so
right, dynamic RAM.
Standard
DRAM,
computer memory. Actually, it's one transistor and one capacitor per cell. They're about 100 angstroms across, and you need to refresh them every couple of 100 milliseconds. And so they already exist. So, but it's electric, right? And the relaxation is just the self-discharge of the capacitor.
Mm.
My question is about the economic reality of competing with a technology like that.
Oh, the economic reality is completely in the sky. I mean, you know, I've spoken to storage people and the first thing they do is laugh, right? Because it's pretty ludicrous that we're going to compete with this technology. But I mean, the main thing is that you need to get, the scale of economy of hard drives is massive. Basically, I think for someone like Seagate, I think they're making a disk in about a second. They're making a disk every single second, I think, something like that, to meet demand. So the real bottleneck is, I mean, we have the size, right? We have the size of molecules on our side. If we can push the science that we're doing, you know, the science is always changing, you know, everyone keeps saying. If we can push the science to get the time scale working, then the real bottleneck is going to be deposition and making fabrication of devices. But, you know, in terms of chemistry, there's a lot we can think about that is nicer than alloys in the sense that we can, you know, chemistry can self-assemble. So you can think about self-assembled monolayers where you just literally spray it or dunk your surface in a vat of molecules and you get a self-assembly process. Now, these don't even have to be monolayers because, you know, already what they're dealing with is some nanometer depths of these films anyway. And as long as you can have a well-defined structure of the material, it's okay. And so if we can get, if we can combine the self-assembly side with the memory side that we're working on, then I think this starts to become interesting.
Thanks.
Okay, more questions? Yeah, you can, Lisa, I asked you.
Hi, hello. Sorry, my camera is not working. Nick, very nice talk. And I think very instructive as well. I was just wondering that not so many people are talking when they talk about anisotropy, right? They're not talking that much about anisotropy of the effective G tensor.
Mm.
But I think it is crucially important in this low temperature regime where you call it like tunneling or whatever, before the thermally activated processes like Orbaha kicking in. So of course we need this high barrier to keep this exponential process far away, but the actual bottle, like the limit is about this very low temperature relaxation, which depends on the anisotropy of the G tensor.
Sure.
Do you know if, yeah, there are more analysis on these relaxation processes in the community?
Yeah, I mean, you've hit the nail on the head that, we know how to make big Auerbach barriers. That's not really the problem anymore. The problem is really suppressing the other processes. So for instance, in these molecules, the reason they're good is not because the Auerbach process is really that great, It's because this Raman process, the lower temperature processes, and the quantum tunneling processes, the even lower ones, are much more suppressed than in, say, materials like this. So basically, it's pushing this Raman part very, very, very far down. And that's the main thing. And that, of course, if we're talking the Raman or the quantum tunneling, the ground state quantum tunneling parts, that's really only to do with the lowest states, the ground doublet, as you've mentioned. So as far as I'm aware, there is no yet good or any correlation that's been done on the effective G tensor, which of course, so the effective G tensor for the Kramers doublet reports on the mixings of the different MJ projections into the ground state. So if you have a pure 15 over plus minus 15 over 2, you should have 20, 0, 0. When you don't have a pure state, which in reality you never really will, you have 19 point something something and 0 point something something. And so the order of magnitude of those is very important, as you say. But I don't believe anyone's made a study on the correlation between those effective G tensor values, specifically the transverse.
I think there are some purely theoretical papers by Chibataru, where they derive all the analytical expressions for the rates depending on the anisotropy of G tensor. So, it's not very popular because the mass is very heavy.
I think I know the paper you're talking about, and yeah, it's a pretty full-on paper. I don't recall there being an expression that came all the way down to the G tensor, but I happily be mistaken to look at it again. But that would be very interesting if there's
I think
analytical correlation.
They're just packed into the other parameters in the final expression.
Okay, it might well be that. But
yeah, another thing that I wanted to mention is the Ilya already said about the work of Lungi and company, and I think it is actually the way forward, where you calculate the phonons with DFT, and there you can actually decouple. So the actual real phonon would consist of the molecular vibrations that you calculate with your DFT CASSCF coupling, spin phonon coupling, and you can actually see the translation and rotation of the molecules as the other contribution to the total phonon. And I think these are the key, because all these phonons due to molecular rotation basically cause all these direct processes, because you have anisotropic G tensor which rotates in the field along particular direction, and that rotation causes the fluctuation in the spin Hamiltonian that drives the relaxation process.
Yeah, I definitely agree. I mean, their analysis and their breakdown of the solid state phonon density into those different components is really, really nice. They've done it a few times now over a few different papers. I really like that. But you're absolutely right. And including all of those compositions is important. So that's where we're going essentially as well, is to the solid state phonon density. And
how long does it take?
Which part?
Like the solid state DFT optimization with the
it's not horrible. I mean, I think we're talking, I don't know, a week or so.
on
Archer with
how many?
With a lot of cores. Yeah, I mean, it takes a lot. It takes a bit of grunt to get them. But the thing is, once you have all the phonons, I mean, so the optimization is one thing. That's actually not so bad. It's getting the phonons, right? Because you've got to do all the displacements. That's the painful part. But once you have them, then you're looking at the big CASSCF problem. Like it's a lot of pain at every level, which is why it's taking us so long. But we're still planning to do it. We have all the phonons now, and we're.
But why do you need more CASSCF than just for one molecule? I wouldn't expect.
Well, you've got more modes, right?
No, you shouldn't need more CASSCF.
Yeah, you do. So so this particular molecule, right? That's not the unit cell. The unit cell has 2 of these. So you've doubled the number of atoms. And of course, your vibrational modes are 3n. So you've got, you know, another 6 times the number of modes. But then, of course...
But you surely can decouple them into the normal mode of the molecule if the molecule is identical, or, you know,
yeah,
can be like inverted according to the unit cell. The other parts are just the...
Can I just quickly intervene, but we have some more like basic questions, and then maybe we can have more advanced. I'm not. You can still discuss afterwards, but I thought maybe we should just see whether there are some more like basic questions. Let's put it like this. And I saw you, Ilya, and I just take the freedom to do the same for you now. So are there still people that have some more basic questions for the single molecule magnet physics? Because I actually had one. So this distribution of relaxation times, is this coming from, and you said, I mean, one part is just different structures, but is it also, I mean, I'm not sure, so is it, can it be orientation dependent or something to the, if you have an AC field along which axis or things like this? So can you have or if you have different relaxation processes that you get a different effective rate or something like that?
All of that's a possibility, right? So relaxation rates are field dependent, and the different processes you have depend on the temperature and the field range that you're in. And they're also orientational dependent for some of them, so depending on the orientation of the field. So yes, it could be partially to do with this, but remember, you're always talking about the magnetization that's of a molecule that's projected on the external field axis. That's where you're magnetizing along. So for the molecules that say have their anisotropy perpendicular to the field, you're basically not magnetizing them, you know, because if you have such a strong anisotropy, their magnetic moment along this direction is going to be nothing, basically. So essentially those will have very quick relaxation times, let's say, because they're not really magnetized. So it is partially to do with this, yes. But the majority of the things you're actually measuring are stuff that is basically aligned with the field. So that is part of it. And of course, there are competing relaxation processes that happen, different fundamental spin-phonon interactions, or whether it's also quantum tunneling or whatever that's going on. But all of those essentially should be combining, because those are all very fast processes. The spin, you know, the spin phonon collision rates that we're talking, so the tau naught that sits in front of this is on the order of 10 to the minus 10, 10 to the minus 12, right? So the timescale is very, very quick compared to the AC fields that we're actually applying here, right? So AC magnetometry is on the scale of, say, 0.1, 0.01 hertz up to, say, a few kilohertz. I mean, there are some people who can do up to megahertz AC, but that's still not 10 to the 12 or something like this. So the timescales of the electronic spin phonon processes are much, much, much faster. So basically, we imagine that all the phonons are in equilibrium, and all these processes are going very quick. So that essentially everything is, while there are competing processes, they all will overall give you one measurable rate. That they all combine to give you one rate. That's the general thought, but of course, that could just be a bad approximation that we've all had. So it could be any of these things.
Okay. Thanks. Then more questions? If this is not the case, then I would say Ilya and Lisa, go ahead with your discussion.
The position may continue.
So to continue on Lisa's subject, I mean, all these phonon calculations, right, they assume that the motion, that the quadratic approximation is a good approximation, which for all of these motions, it pretty much never is. So yeah, it's, I mean, the heroic work from Lungi and from you guys, it's always gonna be very approximate, even if computationally heavy. It's just the spectral power density is never gonna come out right.
No, I agree. But you can access, so for instance, in the thermoelectric community, there's a lot of good stuff that looks at the anharmonic contributions. And these These are very, very expensive calculations to get the anharmonic phonon spectra, but they're not impossible. And so I do hope that there's one
day, yeah,
one sort of, you know, just throw everything you've got at it calculation that you can do to pull these out. And so
I like the fact that you are stealing the widths from the infrared. Somewhere that you had this on some slide. You had the Fermi golden rule with the infrared line widths on it. I had a question about that. This one. Surely the product of the delta function and the rho here just simplifies into the rho of delta EIF minus H omega, right?
Yes, of course it does.
Yeah, so okay, I was just sitting and wondering whether maybe a reason you've left it unsimplified.
Consistent with previous literature so people know what's happening.
Mm-hmm.
Yeah.
Yeah, so I think that this one equation is the core of the matter, and I'm fairly pessimistic about quantum chemistry ever hitting it to better than an order of magnitude.
Well, if we can only get an order of magnitude, then maybe we have to suffice with that. But I'm optimistic that once we can accommodate the solid state stuff, we'll get a slightly better representation of this, because we are still yet to go past gas phase. So I'm hoping that it works out. But you may be right. There may be way too many approximations, way too far off. Who knows?
Yeah, but I think there is also a way from experiment to sort of meet us in the middle. In terms of, for example, in all these computational approaches, we completely forget about the coupling between the centers, dipolar coupling, exchange coupling, which are crucially important at very low temperature.
Mm-hmm. Maybe causing your relaxation.
And when you actually see an experiment, when you dilute magnetically these ions, you see the order of magnitude jump in this tunneling curve.
Yeah, absolutely.
Well, sometimes it's just unfair to compare these calculations that do not account for that with experiments that actually have this effect.
Definitely, but you know, we're still not down at that low temperature region yet. Once we get there, then absolutely we need to consider dipolar coupling. I would argue that super exchange is probably very small because these are not covalently bound between different metal ions. So I would imagine that it's mainly a through space dipolar process. But
yeah.
And that could be included. You know, we could think about doing that in some way or another.
Yeah. But in order for you to approach the low temperature, you really need to work out these phonons and.
Oh yeah. So to just follow on from what I was about to say before is we're also looking at the and why it's taking so long is that we're looking at the oh, my words have lost me, the dispersion of the phonon modes in reciprocal space. So with phonon wave vector, and so essentially for those of you who don't know solid state phonons too well, I assume other people are still around listening. What you have of course, is phonon modes that do distortions in unit cells that are next to each other, but then you could have those distortions moving in counter directions, right, with different unit cells in different vicinities. And those are different wave vectors of a given phonon mode. Essentially, in reciprocal space, you can think about the different unit cells. In real space, we start talking about propagation of phonons through as plane waves through crystals. So, and with different wave vectors, so that's how different unit cells are doing this motion periodically, or which direction a given phonon is traveling through a crystal, so same sort of stuff, you get different energies. And so how these curves change energy as a function of dispersion, as a function of wave vector, is also important. And this gives rise to not only the width of the effective, so for instance, in IR, this somehow contributes a little bit to the peak, or sorry, not in IR, in INS, this contributes to the width of the peaks, but it also is obviously very important for relaxation. So considering phonon dispersion, so across reciprocal space, so not just gamma point phonons, right, across everywhere, means there's a lot of stuff to do.
Yeah, but I don't think that you should look so into details in all the phonons, because most of them are irrelevant for your relaxation processes. So you need only those phonons that modulate your spin Hamiltonian.
But that's not true, because right? Because we know at high temperatures, it's the higher energy ones, the intramolecular vibrations, right? Because this was a gas phase calculation, for instance. So we only have intramolecular high energy vibrations. And from this, we're getting pretty close to the Orbach regime. So
I disagree with that, because you assume that at low temperature, your molecular vibrations are inactive. But that's not true, because in these low-lying phonons, which are like couple of wave numbers, when the molecule slightly rotates, it does not rotate as a rigid body. It involves some of your molecular vibrations, which are maybe strongly coupled to the spin Hamiltonian.
Oh, okay, so you're talking about the decomposition, right? So at this point, I'm not even worrying about decomposition. I'm just getting the entire phonon spectrum, and I'm going to couple it to the spin state. But
that's a lot of work. And
of course, it's a lot of work. But we have, okay, then, Lisa, how would you describe the section here when you have the crossover between the Orbach higher energy phonon process and the Raman low energy 2 phonon process, where you have them competing at similar timescales?
I would recommend a good pair of running shoes for a problem like
that. We are not searching for easy ways out.
I mean, you basically, if you're trying to simulate the entire thing, you can't just throw one section out. I mean, we could do a truncation and say, look, there is a threshold of the largest energy gap we have is X, so we don't need any phonons that are higher in energy than X. But essentially, that's all we can do, because everything below that is possibly going to be relevant, and how they couple in first or second order is possibly important. And so if we're trying to do what Ilya is suggesting, is get closer to experiment, we shouldn't make that approximation, especially when we know that these different mechanisms are going to be competitive on similar timescales.
Yeah, but I think like worrying about the actual widths of the phonon life, like, you know, this widths of your distribution is the last thing to worry about. So far, I think you can assume the lifetime of a typical phonon and just go again with this.
Yeah. So
that's going to be a good approximation. But I think the real key to this low temperature is to decompose those phonons into the translation, which is not important at all, rotation, which is crucially important, and the internal modes of the molecule, which some of them are actually very important. That I think is really, yeah.
I don't disagree with you, but I would also say that you don't have to do that decomposition, right?
But then you end up with thousands and thousands of calculations to do.
Yeah, I'm okay with that.
Actually, Nick, I have another question. Because it's called signal molecule magnets. So are there some actually signal molecule like measurements on, I don't know, relaxation rates, etc. on this?
There's been stuff, for instance, on surfaces, but these are still, these are still ensembles of spatially separated single molecules. So it's not really a single molecule measurement. The only truly single molecule stuff has really come from Wolfgang Wernsdorfer, who's been doing terbium bisphenolcyanine for many years, which is this double-decker type molecules. And so you have, that's an okay single molecule magnet, let's say. And he's done a lot of measurements of that in gold break junctions, on carbon nanotubes, and I think he's done a few other ones. But for all intents and purposes, he's not measuring relaxation rates. He's not using this as a single molecule magnet.
Relaxation rate's an ensemble property by definition. So on a single molecule, it plainly doesn't exist.
That's right. You have a single population. Your molecule is in a state at a given time.
And all this quantum mechanical horror about the measurement problem kicks in, right? You measure it and it's somewhere else.
Yeah, but there are single molecule experiments that utilize these states. So, for instance, Wolfgang's done all this really nice EPR work essentially on this molecule, where you do a. I can bring up the slides. I've got it in a presentation for my students if anyone's interested. Where is it? Teaching. Lecture 8. Where are we? Here we are. So if I do a different share, that should put it on. There you go. Okay, so down to here. So this is the sort of system that Wolfgang's been working on. So this is the molecule here, terbium bisphenolcyanine. It's got an easy access type magnetic anisotropy. It's a good single molecule magnet, and you can put it in a break junction, something like this, and you can essentially measure the conductance of this thing, and it's got a magnetic field, vector magnetic field. This is all in a dilution refrigerator at some millikelvins. I don't know. Oh, there you go, 80. There you go. It's very nice and cold, 80 millikelvin. And so what you have is essentially, you don't have a Kramer's doublet. This is a non-Kramer system. It's J6 for terbium-3. So you have an MJ plus minus 6 ground state that actually has some slight avoided crossing near zero field, being non-Kramer's. And terbium has a 100% I3 halves nuclear spin. So you have this kind of hyperfine pattern. There's also quadrupole splitting, which is known for this. And at each of these avoided crossings for these different hyperfine states, you get quantum tunneling. And so this is essentially when you have a very fast change in magnetic moment of the sample as you traverse adiabatically this avoided crossing. And so you get a essentially spin up here goes to a spin down on the other side of this. So if you sweep slowly enough, you get this transition. And it so turns out, sorry, this is for my students, so I've got a lot of stuff. And so this is basically the schematic of the experiment. You put an electron on as you're doing a conductance measurement that sits on the phenolcyanine ligand. That couples via exchange coupling to the total angular momentum of the terbium, which is then coupled via hyperfine to the nuclear spin. So you get this sort of two-stage decoupling, as Wolfgang puts it, is your experiment. And so, right, and so this is the conductance as a function of magnetic field. And you see jumps in the conductance at different field positions. And this happens when it does these quantum tunneling steps. So it turns out that the conductance of that electron that's jumping onto the molecule and then jumping off depends on the magnetic moment of the molecule. And that depends on your sweeping the field. And so what you can do is build up this, and he's very, very nice histograms in his presentations showing that this is really robust and that these field positions are super well defined. And so these give you these avoided crossing positions. And so this is a single molecule. It can only be in one of these states any particular time. So when you run one of these field scans and you perform a conductance measurement, it will jump at one of these positions and only one of them. And then when you sweep back, it'll jump at a different one. But what that means is that as soon as it has done this jump, you know exactly which nuclear spin state it's in. It's in one of them and you know it. So this is the initialization of a qubit, essentially. Okay, and so these states live long enough that you can control them coherently, and you can show Rabi oscillations. I don't know if I have the schematic that does it. Oh, I don't. He's got a really nice schematic because he's done this presentation lots. But the different nuclear spin states all have different frequencies. Obviously, they're you've got quadrupole splitting between them, and so you can drive transitions, Rabi pairs between any of the I think there are 3 different pairs he can drive them between. And that's what he's showing here. So he's essentially driving, so setting the initial state and then driving transitions between the 1 and 0 states to drive the population to equilibrium, or doing other fancy things. And so these experiments is an implementation of the Grover algorithm for picking out a spin state from a mixture. So he starts from a superposition of 3 different nuclear spin states, and then depending on the pulse sequence of the Grover that he applies, he can either pick out one of the 3. And that's in the nuclear spin of a single molecule magnet in a break junction via conductance. So that's sort of the best single molecule experiment that has been done on these. But again, it's not a relaxation measurement because, as Ilya says, that doesn't exist technically, and it's also not exploiting the massive not exclusively exploiting the massive anisotropy of these systems.
Okay, thanks again, Nick, for this also extended discussion. I think I just stopped the recording here.